In this video you will see how linearization can change the solutions of a differential equation. Here we have a pendulum. A mass is attached to a rod which is suspended from a fixed point. If there is some air resistance, the oscillations are damped. First we derive the differential equation that describes these movements. Let theta be the angle between the rod and the vertical. Assume that the rod is weightless and let its length be L. The motion is determined by two forces, gravity and friction. Decompose the gravity force, mg, into a component along the rod, which is compensated for by the tension force in the rod, and a component along the circle, minus mg sine theta, which will cause the oscillation. We assume that the friction force is proportional to the velocity. The arc length, s, equals L times theta. So velocity ds dt, which is written as s prime, equals L times theta prime. The friction force can be modeled by minus CL theta prime. Apply the second law of Newton. F equals mass times acceleration, which equals ml times the second derivative of theta. Combining these expressions and rearranging them gives us the differential equation for the pendulum. For convenience, we rename C over m as gamma. This differential equation is nonlinear because of the sign in the third term, and an analytical solution is not straightforward. So we approximate this equation by linearization. First, we rewrite this second-order differential equation as a system of two first-order ODE by introducing the angular velocity omega as the derivative of theta. Of course, the system is still nonlinear. In an equilibrium point, derivatives theta prime and omega prime have to vanish, so omega has to be 0 and sine theta has to be 0. So 0, 0 is of course an equilibrium point, the pendulum hanging still. Point pi 0 is also an equilibrium point. Then the rod stands still directly above the suspension point. This must be an unstable equilibrium. All points k pi 0, for k an integer number, are equilibrium points. For example, when k equals 2, the pendulum has swung once over the top and then hangs motionless. Now linearize the system around equilibrium point 0, 0. First calculate the Jacobian matrix. Introduce new translated variables u and v, which are simple in this case. The linearized system becomes the derivative of u equals a simple matrix times vector u. The eigenvalues of the matrix are complex with negative real parts. So 0, 0 is a stable spiral point. Here you see the linearized pendulum in the phase plane. The solution curve spirals towards the origin. And the graph of u versus time also shows a damped oscillation, just as we expect. Now compare the linearized solution in orange with the original nonlinear one in blue. You see that the linearized pendulum is moving only a little differently from the original one. The same in the phase plane. The linearized solution is a little ahead, but the approximation is good. You see the same in the behavior in time. Note that to calculate the original solution we had to resort to a numerical method. The amplitudes we saw were small, and that is precisely where sine theta is well approximated by theta itself. Let's now see what happens when we use a larger initial angle. You see that the linearized solution is rather different, but later on, when the amplitudes have become smaller, the solutions resemble each other. And once again, different in the beginning, but resemblance when everything is damped. Now we take a large initial angle and also a large initial velocity and see what happens. The original pendulum goes once over the top and ends up in equilibrium point minus 2 pi 0, while the linearized pendulum cannot cross over to another equilibrium point. Conclusion: the linearization is not a good approximation at all when the solution is far away from 0, 0. Now we change the friction term into another one that is used often. Assume that the air resistance is not proportional to the velocity, but proportional to the square of the velocity. In the first order system, the friction term changes into minus gamma omega squared. 0, 0 is still one of the equilibrium points. The friction element in the Jacobian matrix is now minus 2 gamma omega. So in the system linearized around 0, 0, the friction element vanishes. And the eigenvalues of the matrix are purely imaginary. Compare again the linearized solution in orange with the original one in blue. The original pendulum is damped, and 0, 0 is a stable spiral point. In a linearized system, however, the eigenvalues are purely imaginary, and 0, 0 is a circle point. The types of the equilibrium points are different. Because the damping term is in the differential equation is quadratic, you cannot see the damping in the linearized pendulum. In this video you have seen how well solutions of nonlinear differential equations can be approximated by linearization. You have to stay near the equilibrium point for a good resemblance. You have also seen that by linearizing a system you lose all quadratic and higher order effects, such as quadratic damping. As a result, an equilibrium point may change its type when you linearize a system, for example from a stable spiral point to a circle point.